So again, this might look a little bit different by the time you get to it, but I suspect it will look very similar. So what's in this file is just an instantiation of the solution for a particular lab, specified here as a slide number. In case we do change that mechanism by the time we get to the lab, read the comments that might be here. But at this point, you specify a lab number, rather a slide number, corresponding to one of the labs. And you can see the slide numbers in the presentation videos. And we also have visualization enabled for the CPU. So this is basically opening up the final implementation of your RISC-V core. And the diagram takes a while to generate because you've developed a substantial amount of code at this point. But we should get that shortly. And I guess in the meantime, we'll take a look at the visualization of the core. So again, this is the complete CPU that you've implemented at this point. And basically, as you walk through the lab exercises, you'll see this, essentially. But early on, there's no functionality behind what you're seeing in the visualization. And so the PC won't be incrementing, the instructions won't be decoding, and the register file and the memory, if there's one, will not be updating. But just to walk through what's here. So this is a representation of the instruction memory, showing the instructions contained in that memory in their disassembled form. This arrow here is your PC, and I can step through and see the PC start to increment over these instructions. And here I've reached a branch. We're implementing a pipeline CPU, and you'll notice that the PC continues after the branch, as you'll learn about in the labs, and then the machine realizes, hey, I went too far, I need to jump back to the proper branch target and continue on my way. And you can see that loop behavior in the visualization as we step through the simulation. We also have the instructions here in their binary representation, so you can see the literal values in memory and relate that to your decode logic. And we see the instruction that's being processed. And this one's gray because it's on bad path, meaning it's the machine was executing the wrong instruction and realized that later, so it's shown here in gray. But then we find the right branch target, and we're executing this add instruction. And we can see how that add instruction is decoded by our machine. The source registers, immediate value, and the values in those registers. So we're seeing that we're adding these two registers containing a value of 3, each with 3, resulting in a value of 6. And the result is written to R14. We can see that here in the register file. R14 is written. It used to be 3, and it's updated with a value of 6. And we can see all these register file writes happening as we step through our program. All right, so again, as you start out your labs, there won't be any functionality behind the visualization. And as you step through all these pieces, you'll start to see the PC move, you'll start to see the instructions decode, you'll start to see the register file update as you incorporate that logic. Diagram here timed out. So I have cheated. Magic of time lapse here. So I've gone in and changed the solution. Let's make this a little bigger. To represent the solution for slide 50, whatever that happens to be. A little bit less complete CPU probably, and that managed to generate. We'll do the best we can to make these generate properly, but undoubtedly you'll run into situations where either the diagrams time out, we're going to have 80 or so students working on this platform all at the same time. So undoubtedly the machine will be heavily loaded and you'll get timeouts. Also, you may run into situations where where the diagram doesn't generate at all. That can happen. The tool's not perfect. We've tried to make sure that if you're following along with the instructions that the diagrams do generate, but You might run into situations where you're just stuck. In that case, you get the waveform to debug and the visualization. So again, you can use the reference solutions here to understand what the logic is supposed to be doing. If you get stuck on a particular syntax, can't understand how this expression is supposed to work for a particular part of the exercise, hover over it, see the logic expression, try to understand timing issues and whatnot. How many flip-flops am I supposed to generate? Compare this diagram with the diagrams that you're getting. Try to figure out what you may have done wrong by the differences in the diagram. Again, the code is hidden, so in navTLV, you're going to get this error saying, we're not going to let you see this code. And similarly in the log, we're not going to write these output files for this protected example. But you get the visualization to see the behavior that you're supposed to get. And you can, similarly investigate the waveform to understand what you're supposed to be seeing, the behavior you're supposed to get, compare that with your own. You can also, so in the waveform here, there's this CPU viz pipeline. These are all the signals that are used by the visualization. So you can actually use this to help understand what's being represented in the visualization. All right. All right, back to the slides.